Good afternoon, ladies and gentlemen. Today, this video is going to be going through the problems to prepare for practice C homework in chapter 5. But before we do that, we need to understand what is potential energy and what the difference is between gravitational potential energy and gravitational force. So I draw your attention to this picture here with the elephants, and you are already familiar with gravitational force. So this little elephant is on the ground. So we know that the force, and you see the arrow pointing down, would be his mass times acceleration due to gravity, 9.81 meters per second squared. So that's when he's in the ground, but that is just a force. But there's energy when you go to a higher altitude, higher level. So the same elephant is up at a little bit higher. So this elephant has more gravitational potential energy because it's on higher ground. So why is that? Because the definition of gravitational potential energy is mass times gravity, acceleration due to gravity, times the height. So it's the mg times the height. And that will give you the potential energy. So up here at this height h, there's a potential energy. Again, the units of energy is in joules. But down at what we're considering zero height, the potential energy would be zero because the height is zero, mgh, h is zero. So let's look at this other picture here. This one right here. Now, we have two different skiers. See if I can make it bigger. We have two different skiers here. It says that the green one is heavier. So the heaviest of two objects has the same height. They're both at the same height. They can move this way. They're both at the same height, but they have different mass. So this green one is heavier. It says the heaviest of the two objects at the same height has the greatest gravitational potential energy. So the green skier has more gravitational energy because he weighs more. An analogy for you would be if you're sitting down and a small child falls on top of you, you're going to feel the force, the energy of that small child, but it's going to feel a lot different if it's an adult, someone with a lot more mass. All right, now in this picture here, draw your picture of this girl holding onto a ball at a certain height from the floor. So this height, that would be our h. So there's potential energy. So this ball at this height has potential energy. So notice the subscript G is for gravitational. So this is potential energy, gravitational potential energy, which is mgh. Once it starts moving, it's not potential energy anymore, it's kinetic energy. And the kinetic energy, as you learned, is 1/2 times the mass times the velocity squared. So you can see when she lets go of the ball, that potential energy was transformed into kinetic energy. All right, now we're not going to be talking about it today, but I also have an example here of another kind of potential energy, and this one's called elastic potential energy. Typically, there's a subscript of a lowercase e, where here there's a G for gravitational, and this one's elastic. And that has to do with how much energy is in a spring, boing, before it pushes out, or when you squish it in. So we'll be doing that and probably a lab on that later. Last thing I want to talk about is conservation of mechanical energy. So mechanical energy, now we've been introducing you to kinetic energy when something's moving, and the potential energy, the energy it will have because it's at an elevation of height. So conservation of energy says that the initial energy is equal to the final energy. So the initial energy is its initial kinetic energy plus its initial potential energy, and that's equal to its final kinetic energy plus its final potential energy. So let me unzoom here. And so I'll be upload this sheet for you to review and to take a look at. The difference between gravitational potential energy and gravitational force has to do with the height. Because you're at a height, you're going to have more energy. And it matters on the mass. So here's the formula now for potential energy. This would be gravitational potential energy. And now we're going to be moving to how potential energy then can be converted to or transformed into kinetic energy. And that there is a conservation for the most part. Some of it gets lost in terms of heat also, or sound. That's energy also. But besides heat and sound, the kinetic and the potential energy will be equal to the final kinetic and potential energy. All right, so now what I'd like to do is switch over to the textbook. It'll do that for us. Let's see if it'll do that for us. It did not. Okay, so I'm going to have to do it the old-fashioned way. All right, here we go. So we're going to do our first problem. All right, I got a problem here. I need to switch. All right, let's stop. All right, here we go. So we're looking at preparation for problem C. So the problem says, we have a diver, 50-kilogram diver, steps off a diving board and drops straight down into the water, probably a pool. The water provides an upward force, net, of 1,500 newtons. So 1,500 newtons, the water pushes up. If the diver comes to rest 5 meters below the water surface, what is the total distance between the diving board and the diver's stopping point underwater? Okay, this is probably a good problem to read more than once. I'll try to show you my picture that I came up with. All right, here's my picture I came up with. So I have a diver on the board, and I didn't write this down. His mass is, the mass of the diver is 50 kilograms. And he steps off the diving board and he drops straight into the water. Can't see the water here all the way down. And the water provides an upward force, net force of 1,500. So I showed that this responds by pushing it up 1,500 newtons. There's the force response. If the diver comes to rest 5 meters below, so this is where he ends down here, and that is 5 meters below the surface of the water. And they want to know, what is the total distance between the diving board and where the diver stopped? We want to know this whole distance. So if we call this H, from here to here, from the ground to the level of the diving board, we want to know what deep D, which is 5 meters, plus H is. That's what we want to know. So let's see, we want to know, what's H plus 5 equal to? Once we figure that out, then we'll know what H is. And that'll be the distance that he went, the total distance that he went. All right, so there's a couple of things that you need to know. First of all, right at this point up here, he has a potential energy, his initial potential energy. So let's talk about that. I think I'm going to move the book now. All right. See if I can get rid of that. Okay, that's probably better. All right, so the initial potential energy. We need to know, what is his initial potential energy? Okay, let's write that down. Well, he's got potential energy initially. He's not moving, so there's no kinetic energy. So all his initial energy is, in fact, right here, the initial energy is exclusively potential energy. And that would be his mass times acceleration due to gravity times his whole height, right? So we got that whole height. I'll just write down that potential energy is equal to mgh. Okay, so we've got some height here. That would be the whole height. But let's first of all look and see what's going on. In general, the initial energy is equal to, here, I'm going to put here the whole height. Well, let's go back. Let's do the initial energy is equal to the final energy. So we have the initial potential energy plus the initial kinetic energy is equal to the final potential energy plus the final kinetic energy. All right, so initially he's not moving. Right here, he's not moving. So the velocity initially is 0. If that's true, because remember, I'm right here. Remember, kinetic energy is 1/2 mass times velocity squared. Velocity squared. So initially up here, his initial velocity is 0. And if that's the case, then his initial kinetic energy is 0. So this one here goes to 0. All right, so when he reaches down to the top of the water, this is our baseline right here. Our baseline right here. When he reaches to the top of the water, now his potential energy is 0. Okay, so at this point right here, the potential energy is 0. So we're going to just break this up up above the surface of the water before the water. So we'll separate this part because that part we know is 5. All right, so from here to here, we know the potential energy is 0. So the final potential energy, here's initial. I'll put 1 for initial and 2 for final, even though he really ends up here, down here at 3. But we're going to do just from 1 to 2. So right here, his potential energy is 0 because the height is 0. Everything is based, here's our x-axis, so the height 0. So notice his potential energy up here has got to be equal to his kinetic energy as he enters the water. Okay, again, from this equation, we know that initially his potential energy is 0. And we know right as he hits the water, before he goes in, the potential energy is now 0, because that's our baseline we decided is the 0 mark. So therefore, the potential energy there is 0. So now we're left with the initial potential energy is equal to the kinetic energy final at this point right here. Okay, so what is the potential energy here? It's just mgh. It's his mass times g times this h. Okay, so we know that this right here is mgh. That's that part right there. Okay, and we know from the conservation of energy that that's going to be equal to the kinetic energy right as he enters the water. So notice that's going to be the initial and where this is our final. All right, so what else? So we know that the force of the water, this was the force of the water, was 1500. Okay, so now we get to combine work with potential and kinetic energy. So I'm going to zoom out so you have some more room here. All right, so our net work, what's the net work? And I do hope you guys are reading the book because that's really going to help right now since I don't get to talk to you every day. The net work is the change in kinetic energy. It's the change in kinetic energy, which is the kinetic energy final minus the kinetic energy initial. All right? So now we're at phase 2. The phase 2 part starts right here and we're going to go down. So what happens here? We said that our kinetic energy final at this point, okay, let me see here. The kinetic energy initial as it's entering the water. So we know that the energy right here as he's entering the water is going to be mgh. That's the energy right here. Right here we've got mgh is the energy. And that happens to be our initial kinetic energy. So now we're starting from 2 to 3. So we're going to say here is the initial kinetic energy right here at this point. We know it's mgh, which we can just plug in mass and then 9.81 times, oh, the h we don't know. Okay, so we got mgh there. All right, so then what? Now we can figure out, because of the initial, it's this amount, but when he ends, when he stops right here, the velocity is 0. So I know that the kinetic energy here has got to be 0 because he stopped moving. Okay, he stopped moving and now he's got some, well, let me stick with here. So we got kinetic energy here is 0. All right, so coming here, we have the final, here's our new final. This is our final. Our final one is 0. There we go. So this part right here is 0 because the kinetic energy is 0 when it finally stops down here. And then minus the kinetic energy initial. Okay, and that's our equal to our net work. Well, the initial kinetic energy at this point was the final when he jumped into the water. We already established that that's mgh, right? Okay, so we've got that the work net is equal to negative KEI, which we already established is mgh. Okay, so we got that as mgh. So the initial KEI there is mgh. All right, but we still need another equation, 2 equations, 2 unknowns, right? So let's go back to the other equation for net work. And that is the force times the distance times the cosine of theta. And that's what this part we're dealing with right now, from 2 to 3. All right, so we've got the cosine of theta here is going to be 1. All right, so we've got 1. Well, actually, it's -1. It's 180 degrees. Either way, I want you guys to worry about the magnitude. So we can figure this out that because F net was the same force going down, going up, we already know that it's 1,500 newtons. So the force coming down is got to be the same as the water responding. That's Newton's third law. So I know I've got 1,500 newtons there. And the distance part, this part right here, we know is just 5 meters. They told us that it's 5 meters. 5 meters. And the cosine I've got is 1. All right. So that is equal to work net, which I already established has got to be also equal to mgh. mgh, because all this was equal to the change in kinetic energy. All right, so 1,500 times 5 times 1 is equal to mgh. This is meters, by the way. I don't want to confuse m. This is mass. All right, so I want to solve for what is h. I want to solve for what is h. So I just divide both sides by mg. Divide both sides by mg. Okay, so now I have 1,500. I'll leave off the units. 5 times 1 divided by the mass, and the mass was 50 kilograms. And then g, 9.81 meters per second squared. 9.81 meters per second squared. Oh, I put in the, all right, so we've got h. So we plug that in, and I come up with h is equal to 15.2905 meters. And remember, that's this part from here to here, but the question they wanted to know is how far did he actually travel? So the h plus the d, which was 5. All right, so h plus 5 is 15 plus all that plus 5 is going to be 20.29 meters. And there you go. Okay, so this one is a complicated problem, but it's because of the fact that we're just seeing for the first time conservation of energy. So it was two-part problem. The first part was the mgh from here to here. So because at this point in time, there's no kinetic energy, it's only potential energy. So in this equation here, the kinetic energy is 0. Then we get to here and we realize, oh, the potential energy is 0. This one's 0. So all the energy now has been converted to kinetic energy. So I know what the energy here is. It's mgh, just mgh. All right, then there's the second part of the problem. The second part of the problem, I can't find my other mark. Here it is. Second part of the problem is when he enters the water. When he enters the water, and that one we know the distance is d. So we use the equation that work net, the network, is the change in kinetic energy. So what is the change in kinetic energy between points 2 and 3? It's the kinetic energy final minus the kinetic energy initial. So the kinetic energy final we know was 0 because he stopped moving. But the energy here initially was whatever energy it was when he got to the water, which we'd figured out was mgh. So we were able to determine then that the work net has to be equal to that kinetic energy, which is the mgh, but it's also equal to f d cosine theta. All right, it's going straight down. So we just have the cosine is 1. So we have this 1. The force, they told us what the force was going up. So that has to be equal to the force going down. That's 1,500 newtons times the 5. There's our distance. And then all that was equal to mgh. We divided both sides by mg, and that's how we got h. All right, so we'll probably be doing some roller coaster problems as usually the ones for doing this conservation of energy. Okay, so that was number 21. Let's look at number 22. Number 22 is going to look really familiar to you. Let's see if you can see it here. All right. In a circus performance, a monkey on a sled is given initial speed of 4 meters per second up an incline. Yes, ladies and gentlemen, we're going to be doing more incline ramps and vectors. The combined mass of the monkey and the sled is 20 kilograms, and the coefficient of friction between the sled and the incline is 0.2. How far up the incline did the sled move? All right, so we have a monkey in a box sled. We're going to just draw a box, and their combined mass is 20 kilograms, and they're going up 4 meters per second at an incline of 25 degrees. So we need to draw a picture. Let's see, I think I'll start with the fresh page here and zoom here. All right, what is the question they want to know? They want to know what the distance is, how far up the ramp you went. All right, so we're going to draw. Oh, looks like my pen is dying. It's a bummer. Okay. Oh well. Okay, so I've got the bottom of the ramp, and it said it was 25 degrees, so that's less than 30. There we go. Okay, so I'm going to draw a box, which is going to represent the sled with the monkey in it. All righty. There we go. There's our box. Okay, so we have the mass is equal to, I'm going to write down everything that's given. They give us the mass is equal to 20 kilograms. That's the monkey plus the sled. Monkey plus sled. And then we have that the initial velocity, we have initial velocity is 4.0 meters per second. And we know that this is 25 degrees, 25 degrees. They give you the coefficient of friction. It's moving, so I know it's kinetic, is 0.20. And then it's going to stop. So if it's going to stop, then my final velocity must be 0. And we want to know what's the distance. We'll call that delta x up the ramp. Up the ramp. What is that distance? All right. Well, it seems to me that we're going to need to know an acceleration. So that was the first thing. Somebody asked me, are we going to still need kinematic equations? I said, you betcha. So do we have enough information? Well, at least we can take a look at what equation we're going to need to come up with the delta x. So since I have this, let me see equations for distance with velocities. And I happen to remember, well, actually the first one I wrote down, just to be perfectly honest, I wrote this one down. Remember the V final? And I went, well, that doesn't help me. I want one that gives me a displacement. So I remembered the delta x one. So V final squared is equal to V initial squared plus 2a delta x. Okay, so this is going to help me. I can solve for delta x. Let's see, I'm going to subtract both sides to V initial squared. And I end up with 2a delta x. So if I divide both sides by 2a, then that'll give me my distance. So I need to figure out what the acceleration is. And once I know what the acceleration is, then I can plug it in here and figure out how far it went up. Okay, but of course we need to finish all our vectors here. So let's do that. All right, let's see. I've got first let me put some axes here. There's your x-axis. There's the y-axis. Okay, so I can see my normal force. I have a normal force here. There's my normal force. All right, I have my gravitational force, mg. Let's see, and that's got to be perpendicular with the ground here. So there's my mg. And then this angle in here has got to be 25. 25. Okay, so this thing is going up. If it's going up, then the friction force must be going to the left. Here, I'll put it here. There's my kinetic friction. All right, now I have to break this guy down into its components. See if I can use a black pen here. I have a new one in a package here. Okay, so let's break it down into components. You can already see that the Y one, here's my X one. Probably right there, actually. All right, so there's my X one, pointing to the left. I should make this bigger. All right, so the X one, I'm going to call that the force of gravity in the X direction. That one's opposite to the angle. So that'll be the sine one. So that's going to be mg sine of 25. Okay, now I got to draw my Y one. That's along the y-axis here. Along the y-axis, and that one there is the FG in the y direction. So that one obviously has to be the other one, mg cosine of 25. All right, now they also gave us the mu sub k. So we might as well write that down. What is mu sub k? Well, let's see. Mu sub k, I know I need to know what the normal force is. I know that's in the denominator. And then up here is going to be F sub k. So we need to figure out what F sub k is. And then we need to know F of n, or they gave us mu k. So let's see. Let's look at our vectors. From the vectors, I only see two vectors in the x direction, huh? I only see two vectors in the x direction. Notice that the friction force is going down, but so is the gravitational force in the x direction. They're both going to the left. That's really interesting. They're both pointing in the same direction. So I've got a net force. My net force is going to be the only thing that's left to go up. So let's see. So I've got, it's going up, so I know I have a mass times acceleration. So let's see. I've got both of these going in the same direction. So that has to be equal to the one this way, which is mass times acceleration. The only thing that's going to make it go up. So I get to add these two. So I'm going to say the Fk plus the Fg sub x, they're both pointing in the same direction. That's equal to the mass times acceleration in the x direction. Okay, both these vectors are going down. Something's making it going up, and that would be your net force. Okay, so that's going to be your net force. F equals ma. All right, so looks like I can solve for the acceleration as it's going up, a in the x direction, and that's what I can plug in here, because really I want the acceleration in the x direction here. All right, we're also going to need Fn. So let's see, I only have two vectors in the y direction. I have the normal force, and then I have the gravitational force in the y direction. So those two have to be equal to each other, huh? So let's see if I can write that up here. So Fn has to be equal to this one down, which is mg cosine, put here, Fg in the y direction. Those two vectors have to be equal to each other magnitude-wise, the magnitude. All right, so that's going to be equal to mg cosine 25. All right, so now we know what this guy is here. Now, we know what this guy is because we just figured it out. We know what mu sub k is, so now we can determine what F sub k is. So let me bring this down over here. F sub k, I multiply Fn to both sides, Fn to both sides. So I know my F sub k, my kinetic friction, is equal to mu sub k times Fn. And we already determined that Fn is mg cosine 25. So that's going to be mu sub k times mg cosine of 25. All right, mu sub k, they told us is 0.2. 0.2, the mass is 20 kilograms. Then the 9.81, then the cosine of 25. All that is going to be F sub k. F sub k. So figuring that out, I've got that that's 35.5655 newtons. So there's my F sub k. All right, there's my F sub k. So that goes here. All right, so looking at this, just this part right here, I want to solve for the acceleration in the x direction. So we just divide both sides by m. There we go. All right, so the m's cancel out. So now I know that the acceleration in the x direction is the F sub k plus the Fg in the x direction divided by m. See if I have enough room to write that in. So this one is 35.5655 plus Fgx, that's mg sine of 25. That one I hadn't figured out. So I'll write here 20, that's my m, my 9.81 times, where am I, sine of 25. Sine of 25. And all that divided by m, which is 20 kilograms. So when I punch that out, I get 5.ax is 5.924 meters per second squared. So there's my acceleration. So now I can go back to this kinematic equation to solve for how far did the box finally, how far did it go up the ramp before it finally stopped. All right, so we plug in here, the V final is 0. V initial was 4 meters per second squared. I'm going to go ahead and square it. 16, that's meters squared per second squared, because I know what 4 squared is, divided by 2 times acceleration, which I came up with here, which is 5.94. 5.924 meters per second squared. All right, and I have here, then it comes out to, get my answers here, comes out to 1.35. This is delta x. So delta x is 1.35 meters. So that's how far it goes up. It goes pretty far, 1.35. All right, so let's summarize this problem here. So again, absolutely critical to draw a picture. They said there was a monkey in a sled. So we just draw a box. Everything's in a box. And that box is going to go up a ramp that's 25 degrees. They tell us how much the mass is and how fast it is when it starts going, the velocity, initial velocity. They also told us the coefficient of kinetic friction. All right, and they want to know how far is it going to go up. Yeah, I'm having a tough time getting this to focus. I don't want to go that far up. Okay, so what do? Well, we write down equations that we know, because that always helps us. And then we, of course, have to write all our vectors. This one's really interesting because both the x vectors are pointing down the ramp. And so sum of those two have to be equal to the net force going up, and that would be the mass times acceleration. So like that's how I would get the acceleration. Just divided m to both sides. So we end up with Fk plus mg in the x direction, the gravitational force in the x direction, all that divided by the mass, and that's how we got our acceleration. Then the acceleration we can plug into our kinematic equation, which we already have ready for us for the displacement, and we came up with 1.35 meters. Okay, now that's one way to do the problem. It is not the only way. This to me was the logical way, but the way they had hoped you would do it was using work. So I'm just going to show you guys that one, and this proves that there's always more than one way to solve a problem. And if it's done correctly, you should get the same answer. So here we go. What is work? Net work is a change in kinetic energy. What's a change in kinetic energy? Kinetic energy final minus kinetic energy initial. Okay, what is that? It's 1/2 mv final squared minus 1/2 mv initial squared. Okay, but we also had to realize and also the second one, the second equation, work net is the net force times the distance times the cosine. So we had to use this different angle, this cosine angle here. All right, we'll get to that because it's just going straight up. So there's no angle, so it's going to be 1. Okay, so we have our two different equations for work, but we still had to draw our vectors because we had to notice that the net force is equal to both of these vectors pointing down. Both of these vectors pointing down with these yellow ones. So again, F net is Fk plus Fgx. So went ahead and figured that out. Fk, of course, we still had to use that equation with the coefficient of friction. Coefficient of friction, Fk is going to be coefficient of friction times Fn. And Fn, we realized by looking at the picture, was mg cosine 25. So there's our Fk, and here's our Fg in the x direction. All right, so we have that equation, but this is also equal to, let's see here. What I did here is I pulled out an mg. See how there's an mg in both terms? So I factored out an mg, and I have mg times the quantity 0.2 cosine 25 plus sine of 25. All right, all that is the net force. And notice that the equation of work net is F net times d cosine theta. So the F net is all this thing we just came up with right there. All right, so there's my F net. That's my F net times the d, that's what we're after, times the cosine is really 180. From this part here, we're just going straight up. There's no angle, because from this perspective, you're just sliding up, you're going straight. Okay, so this is just going to be 1. So all that is going to be equal to, notice that here you're only going to have your negative initial because the final velocity was 0. So this work from this one here just gives you this part right here. So all that is equal to negative 1/2 mv squared. So from here, we put this part equal to this whole long thing, and I solve for d. So I solve for d by dividing it all by this stuff right here to make the d by itself. So you had to square your initial velocity and all this stuff right here that we already came up with, and 0.2 times cosine 25 plus the sine of 25, all that still came out to 1.35 meters. So I came up with the same thing. So you will have other problems where this system makes more sense. In this case, it didn't for me, so that's why I didn't do it first. But it's good for you to see it both ways. All right, and that's the end for practice C problems. So I'll see you next time. All right, bye-bye.